Alright, so in the last video we were introducing the definition of a derivative and solving derivatives based on that definition and not with derivative rules. So I want to revisit that with another couple examples. One being the equation of a line. So we know the equation of a line is y equals mx plus b, where m is the slope of the line, and any point on that line is going to have that slope. So I want to do a quick proof using our definition of the derivative just to show that this is indeed true. So our definition of the derivative is f prime of x equals equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Alright, so let's plug in our equation. F of x equals mx plus b. So the limit as delta x approaches 0 of m times x plus delta x plus b minus mx plus b. And remember to put this in parentheses because we're subtracting the entire function of mx plus b. And this is all going to be over delta x. Let's distribute the m into these brackets and this negative sign and rewrite this. So this is going to equal the limit as delta x approaches 0 of mx plus m delta x plus b minus mx minus b all over delta x. And we can immediately see several things cancel. So we have a plus b and a minus b, so those will cancel. And we have a plus mx and a minus mx, so those will cancel. And now we're left with just one term on the top and one term on the bottom. And you can see that these both have a delta x, so those cancel. And we are left with the limit as delta x approaches 0 of m. And so we can plug in delta x, 0 for delta x with m, and since there is no delta x, this is just equal to m. And there we go. We proved that the slope at every point of a straight line is just the slope of the line. So pretty self-explanatory, but just an explanation that shows that this definition of a limit applies to all functions, even the ones that are obvious. It took a lot more work to prove that than what it would take to just look at the slope of the line and know that m is the slope, but it's still important sometimes to demonstrate that those are true. Alright, so let's do one with a higher power. So we're going to do f of x equals, let's do something crazy like x to the 4th. Alright, and so we're going to plug this in. And actually, rather than keeping with f of x and x to the 4th, let's actually use different letters, because this should be valid no matter what we call it. So let's do g of h equals, h to the 4th. Alright, so g prime of h equals the limit, as in this case it will be delta h approaches 0 of g of h plus delta h minus g of h all over delta h. And no matter what we call these, this should still be true. This should still result in the derivative. Alright, so let's start plugging this in. So this is going to equal the limit as delta h approaches 0 of h plus, I even wrote delta x. h plus delta h raised to the power of 4 minus h to the 4th over delta h. And now we are going to want to expand this section here. This is going to be quite an expansion because it's raised to a power of 4. And this is why I didn't decide to choose something like the power of 10. This is why h to the 4th is indeed a crazy problem to do this with, because it's a lot of work. Alright, so h plus, oh my gosh, that's a bad delta. H plus delta h to the 4th is equal to h plus delta h squared squared, or h plus delta h squared times h plus delta h squared. Alright, so using the FOIL method, we know that h plus delta h squared is the square of the ends, so h squared plus delta h squared, and then 2 times the center multiplied together. So 2h delta h. And we have one of these multiplied by itself, so we have to multiply this by itself. So 2h delta h plus delta h squared. Alright, I'm going to use some more colors for this because this is a lot of multiplication. So I'm just going to start from the left and work my way right. No, this is not what I wanted. So h squared times h squared is h to the 4th. H squared times 2h delta h is 2h cubed delta h. And h squared times delta h squared is h squared delta h squared. Alright, moving down the line, 2h delta h is 2h cubed delta h. And then we have 4h squared delta h squared. And 2h delta h cubed. And last one, let's see, this should have 6. Alright, so last 3 terms. So that's plus delta h squared, 2h delta h cubed, and delta h to the 4th. There's a lot of h's and delta h's, and let's see if there's anything we can combine. It does not. Oh yes, there's something we can combine. So this is going to equal h to the 4th, and just cross this out because we already used it. Now we have 2h cubed delta h and 2h cubed delta h. So this is going to be plus 4 h cubed delta h. So cross those out because we already used them. We have an h squared delta h squared. Let's see if there's any more of those. We have one of those. So this is going to be plus 2, since there's 2 of them, h squared delta h squareds. Cross those out, we already used those. Let's see, we do have a 2h delta h cubed and a 2h delta h cubed. So we're going to have 4 h delta h cubed. And then we're left with this guy for h squared delta h squared. And lastly, delta h to the fourth. Alright, so that was this giant guy here. Luckily, the rest of it is pretty simple. It's just one term and one term. So, let's finally rewrite this limit. So all of this is going to equal the limit as delta h approaches 0 of this guy up top, so h to the fourth plus 4 h cubed delta h plus 2h squared delta h squared plus 4h delta h cubed plus 4h squared delta h squared plus delta h to the fourth minus, and then what did we have? Minus h to the fourth. All of this over delta h. And we can cancel a couple things. Not a whole lot, though. So we can cancel this h to the fourth and this h to the fourth because this one is negative and this one is positive. And now we can cancel this delta h on the bottom because each term up top has a delta h in it. So delta h, we can cancel one of these, we can cancel one of these, so that becomes a 2. We can cancel one of those and one of these. So let's rewrite this. The limit as delta h approaches 0 of 4h cubed plus 2h squared delta h plus 4h delta h squared plus 4h squared delta h plus delta h cubed. So we're still left with a lot. However, now we do not have a delta h in the denominator, so we can finally plug in this part of the limit into our equation. And when we do that, when we see that delta h is approaching 0, we can see that this will become 0 because it's multiplied by 0. So will this, so will this, and so will this. And we are left with our derivative, g of h, is just equal to 4h cubed. So that was a lot of work to finally find this derivative. So yet another example why you really don't want to use this method for anything more than very simple derivative problems. It's much better to use the rules. If you knew the power rule, you would be able to know that this was the derivative without doing any work. You could just look at it and know that that's the derivative. Alright, let's do one word problem. So in this case, I want to find the equation of the tangent line to the graph g of x equals negative x squared plus c at x equals 5 with the bounding limits of g of 5 equals negative 5 and negative g of 5, or excuse me, that should not be, yeah, this should actually be g of negative 5 equals negative 5. I wrote that wrong. Alright, so this is a lot when you first look at it. But let's take this in pieces. First, eventually we know that we're going to want a tangent line. So we are going to at least want, actually we might need another, yeah, so let's also say this is the slope of the tangent line. We would need another initial condition to know the equation for the tangent line, which I'll add one extra piece later on, but actually no, we don't. Yeah, we have enough. We have everything we need in this case to find the equation of the tangent line. Okay, So the first thing I want to look at is the equation of the line here. So we have a line g of x equals negative x squared plus c. We do not know what this value of c is just yet, but we can solve for it honestly using either of these. By plugging these in, they should both result in the same value of c, whichever one we choose. Or excuse me, this one and this one, because this is not correct. Okay, so let's plug in g of 5 equals negative 5. So g of 5 here is negative 5. And actually, I'll do this a slightly longer way. So g of negative 5 is going to equal, we're plugging in a negative 5 for every point of x. So this is going to equal negative 5 squared plus c. And we know that this g of negative 5 is equal to negative 5. And so we get negative 5 squared is 25. And this still has negative on the front. Plus c equals negative 5. And solving for c, we will add 5 to both sides. And we will get 20 equals c. And we can do the same thing with the other one, g of 5 equals negative 5, and get the same result. I'm not going to do it because the only thing that would change is this 5 would be a positive, and squaring it would still give you 25. It would be the exact same result. So we have c equals 20. So our equation now becomes g of x equals negative x squared plus 20. And we want the equation of the tangent line to the graph at this point. So the next thing I want to do is to find the derivative of this so I can find the slope of the line at that point. Because if we want the tangent line, we need a slope and we need a point. We would need to use the point-intercept form to solve this equation. Alright, so to take the derivative, g prime of x is going to equal the limit as delta x approaches 0 of g of x plus delta x minus g of x over delta x. And this is going to equal the limit as delta x approaches 0 of negative x plus delta x squared plus 20 minus, and again we're subtracting the entire function, so this has to be in parentheses, minus negative x squared plus 20 divided by delta x. Alright, and this is going to equal the limit as delta x approaches 0 of, and we're going to expand this, so this is going to equal negative x squared plus 2x delta x plus delta x squared. And we're still going to have that plus 20. Now we're going to distribute the negative, and we'll get plus x squared minus 20 all over delta x. And we need to distribute this negative as well. So this is going to equal the limit as delta x approaches 0 of negative x squared minus 2x delta x minus delta x squared plus 20 plus x squared minus 20 divided by delta x. And you can see the 20 and the negative 20 cancel out, the x squared and the negative x squared cancels out, And we are left with the limit as delta x approaches 0. Oh, and this delta x and this delta x cancels out. And that delta x also cancels with one of those. So we are left with the limit as delta x approaches 0 of negative 2x minus delta x. And now we can plug this in for 0. And we are left with just negative 2x. Negative 2x is the derivative of our original function, g of x equals negative x squared plus 20. Alright, so going the whole way back to the word problem, we want to find the tangent line to this equation at this point. So we need the slope for the tangent line, so let's find the slope by plugging in x equals 5 into our derivative equation. So again, a derivative is a function that defines the slope at any point of a function. So plugging in x equals 5 to g prime of x equals negative 2x results in g prime of 5 equals negative 2 times 5, which is just negative 10. So the slope at this point x equals 5 is going to be negative 10. Alright, so now we have a slope and we have a point. Or we can find a point because we have an x value, so we can find the y value in this equation. So to get the point, because we need a slope and a point, we'll just plug in 5 into g of x. So g of 5, actually, sorry, I'll keep writing this on the bottom. So g, again, this is the original function now, not the derivative. G of 5 is equal to negative x squared plus 20, as we found before. And so g of 5 is equal to negative 25 plus 20. And g of 5 is going to equal negative 5. And actually, I think we already knew that from the initial condition, but oh well, we found it again. Alright, so we have a set of points, so 5 and negative 5. Again, because we were analyzing these all at x equals 5, and we found that the y value when x equals 5 is negative 5. And we have a slope, m equals negative 10. And now we can find the equation of the line. We just find this using y equals mx plus b, because we have a value of y, we have a value of x, and we have a value of m. So we can solve for the value of b. And so we have negative 5 equals negative 10 times 5 plus b. And rewrite this below. Negative 5 equals negative 10 times 5 is negative 50 plus b. Now we can add 50 to each side, and we get b is equal to 45. So our equation of the line tangent to our original function at x equals 5 is y equals negative 10 x plus 45. And that is the word problem. And just to visualize it, just to make sure we did this correctly, let me draw a quick graph here. Oh, that is not what I wanted to do. So draw, no, wrong one. There we go. So we drew an axis. And we know this is an upside down parabola because it's negative x squared. And it intersects at y equals 20. And I know that because y equals x squared looks something like this. And if we have a function with a negative of every value, it's going to be flipped upside down. And when we add 20, that means we're shifting it up 20. So this is actually going to be something like this. And we're saying at x equals 5, it's going to have a very steep negative slope. And just by kind of estimating this, let me redraw that. We are going to get a very steep slope at this point. Let's just say it intersects there. So the slope is rise over run. So in this case, if we started here, the rise is actually going to be negative, so it's going to go down pretty substantially and then over. And if we drew this correctly, this would be roughly down negative 10 units and over 1 unit. So this makes sense. This final equation for the tangent line of this function at x equals 5 would be something like this. Y equals negative 10x plus 45. And if we carry this up really far, we see it would intersect the y-axis very high, making this plus 45 value seem reasonable as well.